Lecture 8.6, Motion of a Charged Particle in a Magnetic Field, Cyclotron Motion. The motion of a charge in a magnetic field is broken into two pieces. In other words, there's a superposition between two different motions. One here is that if we have a perpendicular velocity component, it causes circular motion, rotational motion of the charge. If you have a perpendicular and parallel vector components, even though I didn't say it, here I didn't say it, but I really mean velocity components. So it's perpendicular and parallel velocity components. It causes helical motion, which in our case is called cyclotron motion. And it's absolutely beautiful to see in an apparatus. There are three parameters that describe this motion. One is the radius, because it's circular motion, you're going to have a radius. And then there's something called the cyclotron period. But we don't have to talk about the period. We can also talk about the frequency. So the period and the frequency are effectively the same thing. And something called a pitch. And the pitch is only connected to the parallel component, whereas the other two are connected to the perpendicular component. So what I'm going to do is that I'm going to start with the YouTube video so you could see what's called an EM tube. They come in different sizes. The bigger ones are absolutely stunning. So let's start by watching a video. Now, I had to download because this wasn't beautiful. So if you go and you watch it on YouTube, this is what I labeled as a point charge in a magnetic field. So if you want to go watch this, it's almost more useful to download it and then edit it. But what I'm going to show you here is that let's start with the right-hand rule. I'll show you circular motion. And what you're able to do here is that there's a tube. And in this tube, you can rotate it. And as you rotate the beam tube, what ends up happening is that you can change the velocity to be perpendicular only or a component of perpendicular velocity. So let's go share the screen. So what you're seeing here is that this is the tube, and you can see that these are two coils right here. And you have the ability to rotate this tube here at the base. So right now, the fact that you see a circular beam like this means that the velocity is perpendicular. So let's go and look at this thing. So now what you're seeing here is that you have a beam that's straight. So the magnetic field has not been turned on. Now the magnetic field is going to be turned on. And you can see how the beam is changing. That has to do with the right-hand rule. So as you keep changing it, the direction of you, as you keep increasing the magnitude of the magnetic field, you start to see this bending. And if you continue to that, then you get this circular path here. So what I want to show you now is that I want to show you in these images that I copied. And they look like this. It's from this video here. And then here's the images. So right now, what you're looking at is that you have a beam. This is a beam right here. And it's moving in this direction. Now, what this is here is that this is an electronic beam, which means here that the charges here are electrons, not positive charges. So I know that this is an electron beam. So what I want to do here is that I want to pick one point. So if I pick one point, I know that the velocity is going to be perpendicular. So I know that this is a perpendicular velocity. Why? Because I have circular motion. And the other thing that I know here is that I have to have a magnetic force that's causing this thing to bend like this. So now the question is, I know that this bending is due to a negative charge. So what ends up happening is that the only conclusion here from the right-hand rule is that the magnetic field is actually coming out of the board. So as I go around this beam here, you're seeing that my velocity is moving like this, right? So that's V perpendicular. That's V perpendicular. And then this is V perpendicular. And as a consequence, I am seeing that in each of these situations, I am getting a perpendicular force that's causing this circular motion. That's what this picture is actually showing me. And that's why I'm getting this circular motion. So as we already said here, there is one thing that we can visually see here is that we know that this guy has to be the radius of the circle here. Now, here's another thing that I want to show you here is that if I continue to turn the tube, I get an image that looks like this. And what you're seeing here is that I'm getting this helical cyclotron pattern. So the angle here is a little bit hard to see here, but it is perpendicular. So we know what's causing this circular motion is the perpendicular component, right? So we know we have to have a perpendicular component. So I'm going to say that right here, I have a perpendicular component right here. So what's going to cause this helical motion is that I now have a component of the velocity that's parallel. And that's the difference between circular motion and helical motion. So now that we have that, again, if you go to the video on YouTube, it's not that great. I had to really modify what it actually produced. So let's go to the next piece here. We have, so I said that there's two pieces to this thing, right? There's two pieces. And so when I look at the two pieces, it has to be circular motion, and then there's cyclotron motion. So there are two pieces to cyclotron motion. And it effectively is this. If I have a perpendicular component that's not zero, then I have a magnetic force that's not zero, and that's going to create circular motion. So this is what we mean by circular motion. And the second piece now says that I now have a parallel component that's not zero. But what we find here is that parallel components have magnetic forces that are zero. So the magnetic field does not change the parallel component. This is what's known as the drift motion of cyclotron motion. So we want to cover the circular motion first, and then we want to get to the drift. Here we go. So we're going to look at the circular or rotational motion. And of course, this is part of cyclotron motion. So I have to look at it in the context of the whole thing. So let's put the details down. Circular motion has two main characteristics. One, it has a radius. Of course, it's going in a circle, and it has a period. Then we have the period. And by the way, I can also talk about this as the frequency. I mean, even though they mean different things, they really are effectively the same thing. So we then have the period and frequency of the rotational motion of the charges. So for circular motion, I can only talk about the radius and the period. So let's talk about the radius r. Now the radius r is really derived from Newton's second law. So let's look at this thing here. So from Newton's second law, which I typically write as N2L, circular motion occurs when the velocity And in our case, it's going to be a velocity component. And magnetic field are perpendicular. So they have to be perpendicular to each other. So let's start with a positive charge. So in real life, we don't get that many positive charges. We typically deal with negative charges. So what I'm imagining here is that I'm going to have a region of uniform magnetic field. So I'm going to imagine that I have a spot. I don't know how big to actually draw this. So let's just assume that I'm going to draw it nice and big. And in this region, I have a uniform magnetic field. So I imagine that everywhere in here, I have a magnetic field. So if I start to draw this out, maybe I can come in here and just say, okay, I have X, X, X. So that's the direction of my field. So I'm saying that this is my direction of the magnetic field. I didn't define a coordinate system, which is okay. So now what's going to happen is that a charge is going to enter this field and it's going to move in a circle. And let's say that this is a circle that it's doing. Now, I'm going to, so typically when I talk about a charge entering the magnetic field, I imagine that it's down here at the bottom. But then I'd have to really change the picture. So I'm going to assume that for right now, the charge enters right here. And as it enters right here, I now know that my velocity component must be in this direction, which is the perpendicular one. So according to the right-hand rule, if you use the right-hand rule, you're going to find here that the magnetic force for a positive charge is going to point inwards like this. So the fact that it's perpendicular doesn't change its velocity. It only changes its direction. So what I'm seeing here is that here, I'm going to say that it enters the magnetic field here, and then we just adjust everything. And so now that it has that, we could immediately conclude here is that because of this, it's going to have some radius. And now the charge is going to start to move. So if I look at a point here, here, or here, and if I follow the right-hand rule, we're going to see that that right-hand rule says that this charge will continue. So now the next thing that I want to do is that I want to look at not a positive charge, but what's most common. So what's most common here is that we have an electron beam in, at the undergraduate level, it's an EM tube. And that's what we saw with that video here. So if I look at this guy, then I imagine that I'm going to, so the one at our college here actually looks like this. It's actually a blue beam that we actually see. So what do I see here? These charges over here are for a positive charge. So now what we're doing is that I'm going to have to change my colors because I can't draw a blue velocity here because it's going to be harder to see. So in this case, I'm going to change my color. I'm going to say that this is the direction of my velocity here. So the only thing we know here is that there is a magnetic force pointing here, but that's negative. So the question is, what is the direction of the magnetic field? So if I look to the left, if the magnetic field is going into the page, out here, the magnetic field has to be coming out of the page. So in other words, when I look at this magnetic field, that magnetic field is coming out, not in. And so once again, when we're looking at this, you can see very clearly that this is the radius. So look at the difference. The difference is that for a positive charge, the magnetic field goes into the page. For an electron beam, it comes out of the page if we want the same type of rotation. So let's get into the details now. We want to apply Newton's second law to determine the radius, r. So if I look at Newton's second law, we know that it has to be, the net force has to be MAC, which then means it's m velocity perpendicular squared divided by r. But we know what the magnitude of the magnetic field is. So if I look at the magnetic field and I look at this in terms of a magnitude, this will then be Q V perpendicular B, and then the angle that we're choosing always has to be 90 degrees between the two. And then this guy has to equal mass times the acceleration. So if I manipulate this thing, we can then solve for radius r. So if I do that, this is just simple algebra here. If I solve for big R, we could then say that the radius r is then going to be equal to mv perpendicular divided by q times b. So here's our radius. And the thing that we're seeing here is that the radius depends on 4 parameters. So if I start with the denominator, you could see that it depends on the magnetic field. It depends on the charge Q. It depends on the speed V perpendicular and on mass M. So let's go look at that. So we'll take a look at all of these. And when we start to look at these guys, the one thing that we want to pay attention to is that I'm going to use an applet to help us with this. Okay, so let's look at that. So if I look at these details, here's what I'm going to say. So I'm going to look at the magnetic field dependence. And so when I look at the magnetic field dependence, what I'm going to see is that the radius is inversely proportional to the magnetic field. In other words, the radius r is inversely proportional to the magnetic field and the charge Q. In other words, we're really saying this. that the radius is proportional to 1 over the magnetic field, and it's also proportional to 1 over q. So functionally, they have the same behavior. So I'm going to look at both of these simultaneously. So, but before we get to the applet, what should we expect? Well, if I have a weaker magnetic field, that's what I mean by the little b, what would I expect to have? Well, if I have a weaker field, then the magnetic force should be smaller. So, I should have a small magnetic force, assuming everything stays the same here, which then tells me I'm going to have a larger radius, right? I'm going to have a larger radius R because it's inversely proportional to a smaller field. In other words, if I have a velocity that's fixed, and if I have a weaker magnetic field, it's going to be harder to change the speed of this, not change the speed, but to change the direction of it. So it's going to require a bigger circle. On the other hand, we could then say that if I have a stronger magnetic field, then that tells me that I have a stronger magnetic force. And because I have a stronger magnetic force, since the job of a magnetic force is to change the direction of this thing, then what this tells me here is that then I'm going to have a smaller radius r because the magnetic field strength is larger. So let me show you with the app what I'm seeing here. What you're seeing here is that, note that down here at the bottom, I have a charge. I have a mass that's fixed, and then this is the slider for the magnetic field. But now look what I can do here. I can change the velocity of this guy. And now I'm going to have this going into the page. Let's say I choose that. So I'm going to look at this guy and I'm going to just say, okay, how about if we pick some nice number? If I make the magnetic field stronger, then you could see here is that the radius gets smaller, right? So if I started off at, let's say, minus 4 millitesla. So now if I make it stronger pointing into the board, if let's say I go to 8, you could see, or towards 7, you could see that the radius is smaller. That's what I mean by the inversely proportional. The larger the field, the smaller the radius. Now I can do the same thing with the magnetic field. So if I start off with the magnetic field like this, now look what happens. If this is the mass, if I increase the mass, what would happen? Well, it's got to be harder to change its velocity. And because it's harder to change its velocity, it's going to have a bigger circle. So those are the two images that I now want to take back into with what we did. So here we go. So we just talked about the magnetic field. And what you're seeing in this magnetic field is that, note that these two quantities, these are constant. And these guys will not change. And another thing here is that you're seeing a constant speed right here. So the speed doesn't change, the charges and the mass don't change. However, this is a smaller B field. This over here is a larger B field. And you could see right away here that the smaller B field has a larger radius. This one has a smaller radius. And that's what we expected to see. That's what we expected to see. So if I go look at the mass dependence, now I said the mass, I meant to say the charge dependence. We can see that the charge is also inversely proportional to this thing. So then I could come over here and I can repeat this process. So it's got to be exactly like the magnetic field. So now here I have the charge dependence. So in this case, the radius r is inversely proportional to the charge. And mathematically, we see here is that that's where I get that Q difference. So since this is so similar here, I'm just going to copy this and modify it. But it has the same behavior here. So if I come in here and I put this in here, I just have to modify it just a little bit. And the way I modify it is that I now say, instead of a weaker or a stronger field, what we say here is that this is a smaller charge, little q. And then I'm going to go to a larger charge, which has a bigger charge here. But as a consequence, if I have a smaller charge, I'm going to have a weaker force. If I have a larger charge, I'm going to have a larger force. So therefore, the radius, instead of it being dependent upon the magnetic field in this situation, it's dependent on the charges. So once again, if I take effectively the same image that we did with the applet, here's what I'm having right here. So if I look at this guy, what you're seeing here is that you're seeing what? So here, look at the masses, they're the same. So this guy here and here, these are now the constants of the motion. And again, my speed is constant. So it doesn't change. So the only thing that changes then are the charges. So you could see I'm comparing Q equal to 1e versus Q equal to 2e. So if I have a smaller charge, then I'm going to have a larger radius. The magnetic force is not as strong. If I have a larger charge, then I'm going to have a smaller radius because the magnetic force depends on charge. And as a consequence, it's going to make that circle smaller. So if I now go back and I look at in the numerator, what you're seeing in the numerator depends on mass and perpendicular velocity. So these guys are going to behave the same. So we'll look at one of these, and then we'll just conclude with the others what it is for mass. So now we're going to look at the speed dependence. So now, instead of inversely proportional, the radius is proportional to the speed v perpendicular. In other words, the radius is directly proportional to this. So if I have a slower speed, in other words, v perpendicular is small. So if I have a slower speed, then that means here that if I have the same magnetic field, then it's going to be easier to turn. And because it's easier to turn, we then say it's going to have a smaller radius. In other words, the radius, if I have a slow speed, then the magnetic force can act on it in such a way to create a smaller radius. On the other hand, if I have a faster speed, v perpendicular, and I have the same magnetic field, then this is then going to be harder to turn. If it's harder to turn, then that means I'm going to have a larger radius because the perpendicular component of velocity is larger. Now, let's go look at this at the applet. Is that I need to sort of like fix my values. So I'm going to keep it at 1Q. This mass, I'm going to say is just one electron mass, and I'm going to keep the magnetic field at -4 millitesla. So the charge, what I need to do here is that I need to just increase the speed. So the way I increase the speed here is that I just start pulling on this. So if I look at this guy, let's say that this is 0.5, look at the radius of this guy. It's 0.72 meters. So if the speed is this, then I'm going to get a radius that's 0.72 millimeters. Look what happens if I don't think I can double it, but let's try. So as I start to increase this thing, look at that. If I double it, you could see that the radius has doubled. So it's much larger. So now if I look at mass and I look at speed, because they're both directly proportional, they're going to have the same behavior. So let's go back to my notes and let's get the image that I have, which these numbers will be slightly different here, and it's going to look something like this. So here's what I'm seeing here. All of these guys are a constant, right? So if I look at these guys, these are all the same constants, right? They don't change. However, if I look at this guy, this has a slower speed. This one over here has a higher speed. It's definitely bigger. So as a consequence, this is going to give me a smaller radius r. This one is going to give me a larger r. Exactly what we would have expected. So remember, this has to have the same type of behavior for the mass because it's directly proportional. So what I'm going to do is I'm going to copy this and I'm going to come down here and essentially do the same thing all over again. So if I look at this thing, we're seeing here that we have mass dependence. And so since this is so similar to the speed, I'm just going to paste this guy in here and just modify this because it's going to be the same arguments. So here, instead of speed, we talk about mass. So this is directly proportional to the mass. So then this is directly proportional to the mass. So now we just have to modify these guys, but the arguments are all the same. So what do I see? I have a smaller mass. I'm going to have a tiny mass. Whereas if I have a larger mass, I'm going to have a big mass. So if I keep the magnetic field smaller, the same, a smaller mass is easier to turn. Therefore, I can then have a smaller radius because R is being acted on more strongly by the magnetic force. Even though this is the same, I should be careful. It's not more strongly, it's just that it's easier to accelerate. On the other hand, if I have a larger mass, and I should have color-coded these since that's what I've been doing, then for the same magnetic field, it's going to be harder to turn. And if it's harder to turn, then I'm going to have a larger radius because the mass is larger. So if I take my image as we did with the other examples, you'll see that I have this scenario here. So if I look at this guy, we're seeing here is that the charge is a constant. The magnetic field is a constant. And the speed is a constant. So the only thing is changing the mass here. And you could see here that this tells me that this is a smaller mass. This guy here has a larger mass. And therefore, you can just look at the image and it says that this is definitely a larger radius. And this guy's going to have a smaller radius. Just as expected. So the other piece to circular motion of circular motion is its cyclic period, right? Because it keeps repeating itself. And so this period, the cyclic period, is known as the cyclotron period. But we can also equally talk about this in the language of frequency. So talking about period or frequency is not that important. And here's what we know. when a charge moves in a circular trajectory, the repeat time is called the cyclotron period. And only because we're going to be talking about cyclotron motion. It's just a period. Where we can connect the cyclotron period to 1 over the cyclotron frequency. They're just the inverse of each other. So in other words, we typically say that the cyclotron period is equal to 1 over the cyclotron frequency. The periodic motion, and so when I say the periodic motion, I should say here, the periodic slash circular motion is associated with velocity perpendicular. From the definition of velocity or speed, we write that V perpendicular should be how much it traveled distance-wise divided by the time. But if I have a circular path, then this should be 2 pi radius, the circumference, divided by the cyclotron period. So if I solve for the period and the frequency, so if I solve for the period, we get the following thing. We see here is that the period is equal to now 2 pi r divided by v perpendicular. But we just solved for the radius. So for circular motion, we saw from Newton's second law that this was mv perpendicular divided by qb. So if I plug in this value, you're going to see here is that this is going to give me 2 pi times the mass of the charge times the magnetic field, which then tells us that we can write this solution 2 ways. One way, if we want to view this in terms of the period, then this is 2 pi times the mass divided by the charge times the magnetic field, or I can write this in terms of the frequency, which is, of course, 1 over the period, which I just have to inverse what we have up above. So this has to be 2 pi m divided by qb. So talking about one is the same as talking about the other. It's how do you want to count the time? Now, before I leave with this thing, what's surprising, at least I was surprised when I first saw that, this period is independent of radius and speed. It's dependent upon radius and speed. And what's interesting about this is that radius is directly proportional to the velocity. So if I increase the speed, I have a higher radius. If I decrease the speed, I have a lower radius. So these guys are effectively acting independently of the radius and velocity. As long as, I mean, there's a technical issue that we could talk about this, but that really is the case here. I find this very surprising. It turns out that all particles with the same charge to mass values or ratio rotate around B fields, B field lines, I guess, with the same period. No, we kind of talked about this back in the lab with the EM tube, the Thomson tube. Okay, let's go to the last piece. So now we want to talk about the second piece of the motion, the helical slash cyclotron motion. What differentiates circular from cyclotron motion is the parallel velocity component. So let's draw this picture here. So I'm going to have to worry about length here. So I'm going to try to, let's say that we have a magnetic field here. And you know what? I think I want more space. So I'm going to move this down a little bit further down. I'd rather be cautious about my spacing. So what I'm going to imagine is that this is circular motion. So what do we mean by circular motion? We have V perpendicular, which is not equal to 0. And that tells us that there's a magnetic force that's then going to act on this guy. So if I draw this, I want to think about my magnetic fields coming down like this. And I imagine that I have a uniform magnetic field moving something like that. So if I look at this thing, if I have a charged particle right here, what is that charged particle going to do? Well, it is going to move in this uniform magnetic field where it wraps around the field lines. So it's going to come over here like this. It's going to wrap around, then it's going to come right back. So this guy has circular motion. And we know this because the only component is V parallel. And I'm going to say once again that even though I may have said it, may have not, but that's kind of what I'm thinking right here. Now I have constant velocity motion. So if I have constant velocity motion, what does that mean? What that means here is that I have, relative to the magnetic field, this guy is not equal to 0, but the magnetic force is equal to 0. So as a consequence, this guy continues to move horizontally and does not get affected at all by the magnetic field. So I'm saying that if I look at these two motions and I add these two, I have no circular motion. So what's going to happen? I have a velocity component that's moving parallel to the magnetic field, and this guy has a constant speed because the magnetic field can't change the speed. So if I now do a superposition of these two fields, what I'm going to get is what we call cyclotron motion. So a cyclotron motion essentially says that I have V perpendicular is not equal to 0, V parallel is not equal to 0, and I look at this motion here. So I think I still have that graph, so let me try to paste this guy in, and let's see how I can draw this up. So the first thing I got to do is that I got to start thinking about does this beam look like? So if I have this beam, what's going to happen is that it is going to wrap itself around the magnetic field lines, but it starts to move horizontally. So it's moving. And so as it's moving, we're looking at this situation where you're seeing it moving to the right. So the one new thing in this whole process here is that now there is a new distance that we have not talked about. This is what's called the pitch. But before I get there, I wanted to show you some images that I found on the web, and they look like this. And you could see how you're getting this helix. Now, to me, it looks like they all have the same pitch. So if I'm looking at this, I'm saying that if I look at the distance from this guy to right here, that distance right there is the pitch. That's how far it travels horizontally. So if I look at this peak here to about that peak, it looks to me like, I don't know, maybe this one's a little bit longer. I don't know, but they seem awfully close to me. But that's what I mean by the pitch right there. So now let's go define the pitch. Definition. The pitch, x pitch, is the distance traveled along the direction of the magnetic field. In one cyclotron period. And that's what we're seeing right here. After one period, that's one full revolution, we're seeing that. So by definition, if I look at the definition of how we define distance, so how do we define distance? Well, it's going to be the velocity times the time. So if I now put this into the language that we're talking about, that means that the pitch is then going to be V parallel times the cyclotron frequency right there, or the period. Now, note, I can write this as the frequency too. That's not a problem. So when I look at what does this pitch mean? Well, look at these cycles that we're looking at. So these guys have to wrap themselves around the magnetic field. Let's say that this is the magnetic field. So I now have two magnetic fields that are exactly the same, just because I copied them. So now I want to look at a pitch. So if I look at the motion of this thing, I could imagine that this guy could really do something like this. So it's wrapping itself around the magnetic field. And then at the same time, I could have another magnetic field that really takes a long time to actually rewrap itself around the field. In other words, this guy has a very small pitch because I must have a low V parallel value. But if you look at this guy here, compared to that one, this is a large pitch. And that tells us that we have a high V parallel value. So it's just telling us more information. Now, a lot of the times what ends up happening is that we are not given specifically the value of V perpendicular and V parallel. It's all relative to a constant. So the common way to determine components V perpendicular and V parallel is the angle given relative to the magnetic field as it enters the field. So suppose I have a magnetic field that's doing this. I'm going to say that that's my magnetic field. And so what I'm going to look at is that this guy is going to enter into this magnetic field. All angles are measured relative to that magnetic field line. So as a consequence, I can break this up into two parts. One part, I can have V parallel, and then I will have also a V perpendicular. So when I'm looking at this guy, what I'm really seeing here is it's telling me that the way I'm going to calculate this here is that if I have V parallel, then that has to be V cosine of theta. This is what they call the drift speed for the cyclotron motion. This guy, V perpendicular, will be V sine of theta, and then this is the circular speed. So you need to be able to differentiate this thing.